Now on to question number 5. In question number 5, there are bonus marks buried throughout the question, and the question itself has a total of 24 marks to it. In question number 5, we have a equivalent of a parallel RLC circuit, except instead of a current source, we have a voltage source, but each of the capacitor and inductors have a small resistor next to them. In this question, we have to analyze the circuit and understand it. So for part A, we ask what is the DC steady-state voltage in terms of the voltage source. And this is a pretty straightforward DC problem where you replace the current source with a short circuit, remove the capacitor, which functionally removes this entire branch, and look at this as a voltage divider. The voltage divider is straightforward. V0 is equal to RL over RS plus RL times the source current. Part B of this question asks you to take the circuit and identify the differential equation for this circuit. While doing so, there's a few simple things to note. First of all, you've got a simple node over here. This is your capacitor current, this is your inductor current, and this is your source current. So the two things we note is, to start with, we have KCL, which tells us that IS is equal to IC plus IL. In other words, the source current splits into two and divides between the capacitor and the inductor. The next thing that we need to note is that we have standard differential equations that we get for a capacitor and inductor. For a capacitor, I is equal to C dVc by dt. For an inductor, VL is equal to L di by dt. If you're going to set up a differential equation from scratch for this system, you might as well make your variables as convenient as possible. So for your capacitor, you use capacitor voltage. For your inductor, you use inductor current. Now, this is fairly straightforward to accomplish. Looking at your KVL equations, in your KVL equations, we've got two standard KVL equations that we can use. What we're going to do is look through each part of the loop, first working through the capacitor loop, then working through the inductor loop. If we work through the capacitor loop first, then we see that Vs minus ISR minus ICRC, sorry, this is the source resistor, minus Vc is equal to 0. And if we look at that second loop, we have Vs minus Is times the source resistance minus IL times the inductor resistance minus VL is equal to 0. Taking these two equations gives us everything that we need in order to set up our differential equation. So working with the first equation, Vs minus IC plus IL times Rs minus ICRC minus Vc is equal to 0. And in this first equation, we want Vc and IL, but we want to be replacing IC with the C dVc by dt relationship. So, rearranging slightly, we get Vs minus ILRS minus, now we're going to join together the Rs and the RC components, and we're going to replace IC with C dVc by dt minus Vc is equal to 0. And now we note that this is in a pretty standard differential equation form. We could end this here, or we can rearrange this slightly to say that dVc by dt, we move this over to the right-hand side of the equal sign. dVc by dt is equal to 1 over C times Rs plus Rc. And then we write down the rest of the pieces that we have left. So these are minus ILRS minus Vc plus Vs. But notice that this is perfect because we have this in terms of our two variables. and our input. Now we're going to work with the second equation. In our second equation, Vs minus IC plus IL times Rs minus ILRL minus VL is equal to 0. And in this case, we're going to be replacing VL. So we replace this by lumping things together. We have Vs minus Rs times C dVc by dt. And then we lump together the two ILs. So minus Rs plus RL times IL minus L dIL by dt is equal to 0. And it's perfectly acceptable to leave this in this form, although it's not quite the standard that we would prefer our differential equation in. But if you want to actually get down to the bottom line, you're going to rearrange and notice that dIL by dt is equal to 1 over L. Play the same game as before, except this time you're going to be doing a little bit more replacing. So on this side, you're going to have negative Rs plus RL times IL. Then you're going to have negative Rs times C. But what you do is you actually replace dVc by dt with the equation up above. So this is going to be over C times Rs plus Rc. Notice that these C's actually cancel themselves out. And you're going to fill in that entire equation from up above. Negative ILRS, negative Vc, positive Vs. And then, of course, you have left plus Vs. Notice that this is your input, this is your input, this is one of your variables, this is one of your variables, this is one of your variables. And in fact, this equation can be rearranged a little bit further, but is completely acceptable as our differential equation. So if you want to spend the time rearranging the equation that you get on the bottom here lumps together all of the IL terms, lumps together the VC terms and the VS terms, where you have slightly more neatly the two differential equation variables and the input variable to your system. And pretty much that's as far as we go with this differential equation. We could work further with it, but of course it requires a knowledge of differential equations and how they work within linear algebra, and that's not something that we've covered within this course. Next, we're asked to go back to the circuit and evaluate a situation where we have certain values for the resistance capacitance, and we want to look at the impedance of the parallel capacitor and inductor branches. So remember that the impedance is a function of frequency, so you can't actually get to a bottom line number, but you can get basically to a structure. If we denote this as your capacitor branch and this as your inductor branch, then what we're looking for is ZEQ is equal to the parallel combination of these two, which is simply equal to ZC times ZL over ZC plus ZL. And of course, you can leave your answer in a ratio of complex numbers because this is a little bit of a messy thing to do. So first, let's write down ZC and ZL. ZC is equal to minus J over theta C. ZL is equal to J theta L, but of course that's without the resistors, so let's add in our resistor. This is equal to RL plus this portion over here, and for our capacitor branch, this is equal to RC minus this portion over here. Taking these together and looking into our parallel equations, we have RC minus J over theta C times RL plus J theta L divided by RC minus J over theta C plus RL plus j theta L. If we work with these numbers, then on the bottom, we simply have RC plus RL plus J times theta L minus 1 over theta C, where notice that on that bottom, this looks an awful lot like our regular resonance equation. Working with the top, first we multiply the real parts, so we're going to have RC times RL. Then we work with the imaginary parts, so J theta C times J theta L. We notice that when we multiply those two together, we're going to have negative J squared. Negative J squared gives us a plus value. And theta L over theta C, notice that the frequency is actually going to disappear out of there. And then we deal with the complex parts. These two multiply, and these two multiply. So let's add J, and then we're going to multiply the two parts. We have RC times theta L minus RL over theta C. Now we actually have a lot of numbers in here, so let's actually deal with the numbers that we have. So working backwards here, ZEQ is equal to, we notice that the resistances are 2K each. So we're going to have, and we're going to leave this all in K. We notice that on the top things multiply and on the bottom they divide out. So if we leave everything in K units, then we're going to have an easier time down the line. And if we do that, then we just actually have some real numbers to work with. We're also going to notice over here that in that case, if we deal with ZL, this is equal to 2 kiloohms plus J times theta. Now L is 500 henries. If we want that in a unit of K, then we have to have 0.5. So this is kiloohms. And let's do the same thing for ZC. Moving this over slightly, again, giving us a little bit more space. This is equal to 2 minus J over theta times 80 microfarads. Well, if we deal with 80 microfarads, we move the K up onto the top, then this is very simply going to be equal to 2 minus J times 12.5 over theta kiloohms. So moving back to our equation over here, ZEQ is equal to 2 times 2 plus, and now we have simply the 500 henries divided by the 80 microfarads, which we're going to have to convert in a minute, plus J times 2 times theta times 0.5 minus 2, and now remember we have already figured out what theta C is, so that's equal to minus 2 times 12.5 divided by theta divided by 2 plus 2 plus J times 0.5 theta minus 12.5 divided by theta. Clump things together over here, and again 500 Henry divided by 80 Henry, which divided by 80 microfarads. If you had that, might actually have been easier to stick with our complex numbers that we started with. So this was actually 0.5 times 12.5, or 6 1/4. So 4 plus 6 1/4 is 10.25 plus j times 2 times 0.5 theta minus 12.5 divided by theta all over 4 plus j times 0.5 theta minus 12.5 over theta. And again, you're supposed to leave this as a mixed ratio of complex numbers. So this is your final answer over here. Part D of the question asks you to extrapolate your DC steady state voltage in terms of your input voltage and to check if your answer matches what you got earlier. And this should actually say in part A, not in part B. So if you take a look at this, then you have to realize that DC occurs as theta goes to 0. So ZEQ of your parallel branch, and remember that V0 is across your entire parallel branch, so you're going to need that. This is equal to, we've got 10.25 plus J2 times 0.5 theta minus 12.5 over theta divided by 4 plus J times 0.5 minus 12.5 over theta. Now it doesn't really help us to have something divided by theta, so we're going to multiply top and bottom by theta over theta. And when we do that, we get a theta in here, theta squared here, this disappears. A theta in here, there was a theta in here that we forgot. Theta squared in here, and this disappears. What we're left with when we've done that is simply the part that doesn't have any thetas next to it. We have J2 times negative 12.5 divided by J times negative 12.5. The negatives cancel, the J's cancel, the 12.5's cancel, and we're left with the 2. So therefore, ZEQ is equal to 2. Well, once we have 2 kilo ohms there, then we can very easily go back and calculate. We have our voltage source, we have 2K, and now we have an equivalent impedance of ZEQ is equal to 2K. Put that together. Therefore, V0, which is the voltage across here, is equal to 2 over 2 plus 2 times Vs, which is equal to 1/2 Vs. Notice that this is equal to ZEQ over Rs plus ZEQ. But ZEQ is actually just that resistance voltage. This is actually the same thing that we got in part 1, which is RL over Rs plus RL times Vs. And in fact, we do match. And it's a good thing it matches. That's what we would expect. In the last part of our question, we're asked to find the steady state signal V0 when our input voltage is a sinusoid with a frequency of 5. So we can take Vs and convert it into a phasor. This is just equal to 10. We know that the sine has to convert to cosine, so that's minus 90 degrees. And this is at an angle of theta is equal to 5 rads per second. Going back to our equivalent impedance, ZEQ is equal to 10.25 plus J2 times 0.5 theta, which is 5, minus 12.5 over theta, which is 5, divided by 4 plus J times 0.5 theta minus 12 over theta. Now, we'll notice that 0.5 times 5 is 2.5. 12.5 divided by 5 is also the same 2.5. 2.5 minus 2.5 is equal to 0. So this is actually our resonant frequency. Remember, that's always theta squared is equal to 1 over LC. In this case, that happens to be exactly where we got our resonant frequency is theta equals 5. So ZEQ simplifies to 10.25 divided by 4, and the complex part disappears, so you can really just write that as 10.5 divided by 4. And if you wanted to put it with an angle as a polar notation, this is equal to 10.25 over 4 with an angle of 0 degrees. As such, if we want to calculate V naught of T is simply equal to 10.25 over 4 over 2 plus 10.25 over 4 times Vs of T. And we can simply take this fraction, multiply it out, or leave it as a fraction. V naught of T is equal to 10 1/4 over, so I'm going to multiply both sides by 4 to get rid of that. So 10 1/4 over 8 plus 10 1/4 times Vs, which is just 10.25 divided by 18.25. And now I'm going to take our original signal multiplied by 10, and now I have no angle to worry about. So this is just the sine of 5t. And of course, I don't need to worry about any transients because I've asked for the steady state signal, not the transient signal. The last part of our question asks, how does this circuit operate differently from the standard RLC circuit? And the circuit operates differently from the standard RLC circuit in a very interesting way. When you reach the resonant frequency, at the resonant frequency, you have a signal that disappears, but at the same time, there's no divide by zero issues. So that's kind of nice, because in your standard RLC circuit, you have an impedance where you're dividing by zero, which creates problems mathematically, and you could have things that go off to infinity. In this case, that doesn't happen. Nothing goes off to infinity, and you have a purely real impedance as long as RL equals RC. So ZEQ at resonant frequency is real as long as RC equals RL, those two resistors are matched. Now, taking a look at this question, going back to the beginning, we want to know how many parts each, how many marks each of these are worth. This is worth 2 marks. This is worth 6 marks. This work up here is worth 6 marks. This work on the bottom is worth 3 marks. This is 5, and this is 2.